So, guys, hello, welcome back. Let's go to the next example, which we are gonna work with the model that we had before for this example. Okay, so in the example 21 that we solved in the class, if you guys remember, again we had two options. Yes, we went first after the transfer functions, and also we went after the integrators. Okay, so let's go ahead and just make a screenshot of the transfer function one first. Okay, and then do the um, integrator one. Okay, so let me just do a better job with the screenshot. Okay, so I think TL was not copied in my screenshot. Okay, so I'm gonna make a screenshot with the whole transfer function here. Okay, and then with the block. Okay, and then come here. Okay, now let's go and make a new file here. Okay, so I'm gonna make a blank model here and maximize this. Okay, and then just bring the screenshot here so I can see everything that's going on in the system. Okay, now again, you see that I need a transfer function, a gain, another transfer function, another gain, okay, and then a summer here. Okay. However, if you look at this one, okay, you see that L and R are still in the problem, okay, but I would have KM and KB as well in the problem, and also J and B. Okay. So you need to basically make a new initial file for all of these guys. So let's go ahead and make another initial file. Okay, so CLC again, clear all of the workspace. Okay, and also I'm going to close whatever that's open here. Okay, so for this part, I would say J is equal to again 1, just for the sake of simplicity. Okay, which is the moment of inertia of the rotor. Okay, and also I would pick a bearing value as 0.1 per se. Okay, and L and S are, L is going to be the inductance of the DC motor. Okay, I'm going to keep it as 100 again. Okay, and also I would have R, which is the resistance of the DC motor. I'll call it as 1 ohm. Okay, and at last, the last thing that I need to add is Km and Kb, which are the motor torque constant and the back electromotive constant. Okay, so Km, I would say that Km is equal to again 1. Okay, and then Kb is also equal to 1. Okay, just some numbers. Okay, you want to run this again, you need to save it. Okay, so it's going to be example 21. Okay, 21, and this is going to be the initial values. Okay, values. Okay, and when you save it, you run it. Now, good, you have everything that you wanted here in the workspace. Now, your workspace have access to these guys. Okay, so let's go back to the Simulink model. Okay, and let's see what we can do here. At this point, what I'm going to do is I'm going to import the transfer function, the gain, the transfer function, another gain, a summer, a summer. Okay, so 2 summers, 2 transfer functions, 2 gains. Okay, so let's go ahead and do that. Okay, so it's going to be transfer function. Okay, here, the transfer function here. Okay, this is the second one. Okay, and then also one junction here, which is the sum here. Okay, and again here, which is my Km. Okay, again in the feedback loop. Okay, and another summer here, another junction here. Okay, so look at this. Now I'm gonna work with these guys. You see that the first summer on the left, okay, you have positive and negative. So double click on this one, okay, and you guys might have seen this, okay, but the straight line that you see here is the spacer. Okay, so basically you're gonna space out signals with this guy. Okay, so I'm gonna just keep the spacer as it is. Okay, and I'm gonna have these guys as plus and minus. Okay, then for the transfer function, I would need to make 1 over R Ls plus R. So the first value is gonna be L, the second value is gonna be R. Okay, so I'm gonna pick L, okay, and then I'm gonna pick R here as well. Okay. And I'm done with this transfer function. Just make it a little bit bigger to show the values for L, S, and R. Okay. And we're good at this point. Okay. And then the gain here is Km. Okay. So just double click on that one. K sub M is inside your workspace. You just click on that one. This one, you need 3 of these guys. Okay. One from for the summer, one from the left, one from the top, one from the bottom. Yes. So from the top, so you need a spacer here. Yes. So from the top, you will have negative, then a spacer. Okay. Then positive, which is going to be the left. Okay. You go counterclockwise. Yes. Then another spacer. Okay. And so basically that's the one that you need to have. Yes. So basically you need spacer. Yeah. Something like this. Okay. If I'm not making a mistake. Yeah. And let's see if that's correct. Okay. So when you apply here, you see that again, this is exactly the form that I wanted to see. Yeah. Okay. The next transfer function is 1 over js plus b. So you pick the values for j and b here and the denominator. And you have these values in the workspace. So you pick these ones, okay, and then click OK. Make this one also a little bit bigger so you can see the transfer. It's not necessary, okay, just for the sake of simplicity. Now this one is KB. Look at this. This is K, underline B, okay, and you're good to go with this one. However, you need to flip this one around. Yes. So for flipping these guys, to rotate these guys, you hold down Control and then R. Yes. So it's gonna flip them around. Okay. Now let's connect them together. Yeah. So we're gonna connect this one to this one to this one. Sorry. To here. Okay. And then also this one to this one. Okay. And the output of this guy is going to go to a scope, probably, just to see the output, what is going on in the system. Okay. And from that scope, you're going to get a branch to the gain. Okay. And another branch to this guy. Okay. Similarly, you can have a source as a sine wave. Okay. And this is going to be your input to the system. Okay. And at this point, your simulation is ready. You can run this. However, you need to have a torque load as well. For this problem, what I'm going to do is I'm going to bring a constant value, okay, of for the torque load, okay, and just to make it a little bit different. Yes. So for this one, I'm happy with the 1 Newton per meter. Okay. You can change this one to whatever source that you want. Okay. And now you're ready. You can run this simulation. Okay. When you run this, it's going to compile. Okay. And it's going to show the signal that it generates for you. Okay. So this is the value of the omega of the DC motor that you have with this sines and cosines functions. Okay. So in the next example, we're going to do the same thing with the integrator. Okay. And also, one thing that I forgot to mention is that if you make these ones a little bit bigger, it's going to also show the gain values that they are using. Okay. It's not necessary. Okay. But if you just want to see them, it's going to be nicer. Okay. Okay. See you guys in the next video.